Every bank transaction you have ever made, every password you have ever typed, every private message, every medical record, every government secret, every military communication that travels through a digital network, all of it is protected by the same mathematical problem. A problem so hard that the fastest supercomputers on Earth, working continuously since the universe began, would not have solved it by now. The problem is called integer factorization, the challenge of taking a very large number and finding the two prime numbers that multiply together to produce it. A 2048-digit number can be created by multiplying two primes in a fraction of a second. Reversing that, finding the two primes from the large number, is so computationally expensive that it is effectively impossible for any classical computer at any practical timescale. This is the mathematical foundation of RSA encryption, the protocol that has protected digital communications since 1977. And in March 2026, a paper published simultaneously by Google Quantum AI and a startup called Atomic, co-founded by a former Google engineer who had been using AI to explore quantum architecture, described something that security researchers at the highest levels of government and industry described with one word: terrifying. Not because a quantum computer had broken RSA encryption yet, but because AI had just shown quantum researchers a path to doing it far sooner than anyone had believed possible. The godlike discovery was not a single calculation. It was a map that shows where the door is, how thick it is, and how much smaller the key needs to be than anyone thought. To understand what happened in March 2026, you need to understand the relationship between quantum computing and encryption. The mathematical problem that makes RSA encryption secure, factoring large numbers, is easy for quantum computers in theory. In 1994, mathematician Peter Shor developed an algorithm called Shor's algorithm that can factor large numbers exponentially faster than any known classical algorithm. If you run Shor's algorithm on a sufficiently powerful quantum computer, you can take a 2048-bit RSA key, the standard length used to protect most internet communications, and factor it in a matter of hours or days. The encryption that would take a classical computer millions of years breaks in the time it takes to watch a few movies. This has been known since 1994. The reason it has not yet happened is that running Shor's algorithm on a 2048-bit number requires a quantum computer with millions of error-corrected logical qubits operating continuously and accurately for hours. The most advanced quantum computers available today, including Google's Willow chip with its 105 physical qubits, are nowhere near that threshold. The scientific consensus before March 2026 was that a quantum computer capable of breaking RSA 2048 was at minimum 10 to 15 years away, possibly longer. The March 2026 paper changed that consensus, not because it demonstrated a working cryptographic attack, because it demonstrated using AI-assisted design tools a new approach to quantum architecture that dramatically reduces the number of qubits required, and therefore dramatically accelerates the timeline. The researcher at the center of this story is Craig Gidney, a cryptographer at Google who had been quietly working on the resource estimates for quantum attacks on RSA encryption for years. In 2019, Gidney co-authored a paper that estimated breaking RSA 2048 would require approximately 20 million physical qubits. That estimate, 20 million qubits, was the number that the security community used when evaluating how long current encryption would remain safe. 20 million qubits on a timeline of 10 to 15 years gave governments and corporations a window to upgrade their cryptographic infrastructure to post-quantum standards before the threat arrived. The 2026 paper used AI-assisted optimization to redesign the quantum circuits for Shor's algorithm with far greater efficiency than human engineers had achieved through conventional means. The new approach reduced the estimated qubit requirement by a factor that brought the threshold significantly closer to what near-term quantum hardware might achieve within this decade. Exact figures from the paper are still being analyzed and debated, but the security community's response was immediate. A researcher at the security firm Cloudflare named Bas Westerbaan, one of the world's leading experts on post-quantum cryptography, described the situation by saying almost every system in the world becomes vulnerable altogether to a quantum attacker if current encryption is not replaced. His words were not hypothetical. They were a description of what the March 2026 paper had moved from a distant future threat to a potentially near-term reality. The AI component of this discovery is what makes it genuinely unprecedented. Human engineers designing quantum circuits have constraints. They think in terms of architectures they already know, optimization strategies they have already explored, design patterns inherited from decades of classical computing. AI has no such constraints. When the researchers at Google and Atomic used AI to explore the space of possible quantum circuit designs for Shor's algorithm, the AI found approaches to circuit compilation, error correction integration, and qubit routing that human engineers had not considered and would not naturally have arrived at through conventional design processes. The AI was not doing physics, it was doing something more dangerous in this context. It was doing engineering. Finding arrangements of quantum gates, sequences of qubit operations, and error correction schemes that achieved the same computational result with dramatically fewer resources. The gains that AI-assisted design produced in quantum circuit efficiency in one research program compressed years of expected incremental progress into months of directed search. And the researchers who published the result were explicit that this was the beginning, not the end, of what AI-assisted quantum algorithm design could achieve. And the former Google engineer who co-founded Oratomic told a journalist that he had been using AI and seeing lots of crazy results. He left Google to pursue those results independently. The paper that emerged from that WORC is now being studied by every major government intelligence agency and cybersecurity organization on the planet. The United States government had been aware of this threat long before March 2026, which is why the National Institute of Standards and Technology finalized the first post-quantum cryptographic standards in August 2024. A set of mathematical algorithms that are believed to be secure against quantum attacks because they are based on mathematical problems that are hard for both classical and quantum computers. The three initial standards, crystals, Kyber for encryption, crystals, dilithium and falcon for digital signatures, represent years of international cryptographic research and analysis. But standards being finalized is not the same as systems being protected. The challenge of transitioning the global internet's encryption infrastructure from RSA and elliptic curve cryptography to post-quantum alternatives is an engineering problem of almost incomprehensible scale. Every web server, every bank, every government agency, every smartphone, every IoT device, every VPN, every certificate authority, every component of the digital infrastructure that modern civilization depends on must be updated. Some of these systems are updated continuously and can be transitioned relatively quickly. Others are embedded in hardware, running in critical infrastructure, or dependent on legacy software that cannot be easily modified. The U.S. government's National Security Memorandum on Quantum Computing, issued in 2022, mandated that federal agencies begin cataloging their cryptographic dependencies and transitioning to post-quantum standards. Progress has been uneven. Many agencies are behind schedule, and the private sector, without a mandate, has moved even more slowly. The concept that makes this situation most alarming is called harvest now, decrypt later. Nation-state adversaries with the resources to store large volumes of intercepted encrypted communications have been doing exactly that, collecting encrypted data today with the intention of decrypting it once quantum computers powerful enough to run Shor's algorithm become available. This strategy is particularly damaging for information with long-term sensitivity. Diplomatic communications, intelligence assessments, military planning documents, medical research data, personal financial information, all of it, if it was transmitted over the internet in encrypted form at any point in the past several years, may already be sitting in databases waiting to be decrypted. The March 2026 paper accelerated the timeline for when those databases might be opened, and the volume of data that adversaries have been collecting under the harvest now, decrypt later strategy, is, by definition, unknown, because successful collection means the target does not know it is happening. The world's most sensitive secrets, communicated through the world's most trusted encryption protocols, may already be in enemy hands, waiting for the key to be built. IBM's response to the March 2026 paper was measured but direct. The company issued a statement acknowledging that the timeline for cryptographically relevant quantum computing had narrowed and reiterating that its post-quantum migration tools and quantum-safe cryptography offerings were available for immediate deployment. Microsoft, which has been developing its own post-quantum standards and quantum-resistant cryptographic products, accelerated its customer communication about migration timelines. The National Security Agency issued a technical advisory in April 2026, directing all entities handling national security information to prioritize post-quantum migration above other cybersecurity initiatives, citing the changed threat landscape explicitly without providing specifics about the classified intelligence underpinning the directive. The specificity of that instruction, accelerate now, not on the previous timeline, was itself a signal that the intelligence community's assessment of the quantum threat had shifted in the wake of the March publications. What makes the quantum AI story genuinely godlike, in the secular sense of that word, is not any single calculation or any specific result. It is the demonstration that the combination of artificial intelligence and quantum computing creates a discovery engine whose pace of progress is no longer bounded by the rate at which human scientists can have ideas. When AI explores the design space of quantum algorithms and finds architectures that human engineers would not have found, the timeline for every quantum computing milestone compresses. Not linearly, as it would if you simply added more human researchers to the problem. exponentially because AI can explore regions of the design space that are inaccessible to human intuition. Google's March 2026 paper was produced by a relatively small team in a relatively short time, using AI tools that are themselves still in early development. As those tools improve, as the AI models trained on quantum circuit design become more capable, the pace of improvement in quantum algorithm efficiency will accelerate further. The encryption that has protected the digital world for nearly 50 years was built on the assumption that certain mathematical problems are hard for machines to solve. That assumption is no longer as safe as it was. The godlike discovery is not that quantum computers can break encryption. That has been known since 1994. The godlike discovery is that AI can build the quantum computer that does it much faster than anyone thought it could, and that the window for protecting the digital infrastructure of civilization from the consequences is narrower than the people responsible for protecting it believed it to be. The quantum transistor moment framing that emerged from multiple research institutions in January 2026 puts the current state of the field in a historical context that makes the March paper's significance easier to grasp. In 1947, Bell Labs engineers invented the transistor, a tiny semiconductor device that replaced the vacuum tubes in early computers, making them smaller, faster, and more reliable. For the first decade after its invention, transistors were expensive, fragile, and limited in their applications. Nobody looking at the first transistors in 1947 would have been able to predict the smartphone in 2007. The capability gap between the first transistors and the integrated circuits that eventually enabled the digital revolution was enormous. But the direction of travel was clear, and once the direction was established, the pace of progress became self-reinforcing. Each improvement made the next improvement easier, more accessible, and faster. Quantum computing is at its transistor moment now. The first functional quantum systems exist. They are limited, fragile, and expensive. But the direction of travel is clear. AI-assisted design is accelerating the pace of progress in ways that compress the timeline between the transistor moment and the integrated circuit moment. The March 2026 paper is not the smartphone. It is the first evidence that the transistor moment has passed and the race to the integrated circuit has begun. And unlike the original transistor race, which played out over decades with no particular urgency, this race has a deadline written into it. The moment when a quantum computer powerful enough to run Shor's algorithm on real cryptographic keys becomes operational, the entire security model that digital civilization is built on changes simultaneously, everywhere, for everyone. The godlike discovery is that this deadline just moved closer, and the world, as one of the paper's co-authors told a journalist from Time magazine, is not prepared. The most immediate practical implication of what happened in March 2026 is something that every individual with a smartphone, a bank account, or a medical record has a stake in. The Post-Quantum Cryptographic standards finalized by NIST in 2024 work. They are mathematically sound. They can protect communications against quantum attacks. But they only protect communications that have already been upgraded to use them. Every message sent today using RSA or elliptic curve cryptography, the protocols that underpin the HTTPS padlock in your browser, the security of your banking app, the encryption of your email, is potentially harvestable and decryptable when the right quantum computer exists. Upgrading those systems to post-quantum standards is not a software update that happens automatically. It requires changes to servers, certificates, protocols, and client software across an infrastructure that touches billions of devices simultaneously. The organizations responsible for managing that transition, governments, banks, telecommunications companies, cloud providers, now have a clearer sense of the urgency than they had before March 2026. Whether that clarity translates into action fast enough depends on decisions being made right now in boardrooms and government offices and standards committees around the world, by people who are reading the same paper that started with a former Google engineer telling a friend he was seeing lots of crazy results. The godlike discovery is not that quantum AI broke the internet. It is that quantum AI showed everyone clearly and undeniably that breaking the internet is now a matter of when, not whether, and that when is coming faster than the world was ready to accept.